Good day, everybody. This is Chris with the Ancient Scholar, and today what I'd like to do is I'd like to talk a little bit about carbon monoxide toxicity or carbon monoxide poisoning. Specifically, the mechanisms of action as we understand them, because there does I've seen this theme that reoccurs where people talk about the toxicity of carbon monoxide, and they are more or less accurate, more or less informed, but they kind of fail to mention the bigger picture. The bigger pictures we know it. There's actually some stuff that we don't understand very well. There are probably some other mechanisms by which carbon monoxide works that we're just not as well aware of. So carbon monoxide. To understand carbon monoxide toxicity, we need to talk a little bit about the hemoglobin molecule. The hemoglobin is, of course, a very exceptionally common protein in the human body. It exists primarily in red blood cells. You have a molecule that's very similar, a protein very similar to hemoglobin, known as myoglobin. Myoglobin is located primarily in muscles. Myoglobin is not a good transport protein, though. It's good at kind of like a little emergency cache or storage of oxygen for when the muscles need additional oxygen in certain physiological states. But I'll focus primarily on the hemoglobin, even though the similarities they're robust similarities between myoglobin and hemoglobin. So hemoglobin is a protein that has quaternary structure. I believe some people enunciate that differently than I do, and that's just the way I enunciate it. So sometimes I have a weird way of pronouncing words, and you're just gonna have to deal with it, as I do. So it has quaternary structure, just like all proteins. A lot of proteins have these several levels of structure, where you start off with the peptide bonds, and then the peptide bonds fold, and then you have your secondary structure, and then you have further folding. Alpha helices, beta pleated sheets, hydrogen bonds are really important there, and you have this tertiary structure, and then you can have these little globulins, globular structures that can then get pulled together to make the protein we call that quaternary structure. And hemoglobin has that structure, and it has these four little globulins, little heme globulins, if you will. That have different units. You have 2 alpha and 2 betas, and the difference between alpha and beta is not really important for this discussion. So if I were to kind of look at a hemoglobin molecule, this is a representation of that, where maybe these are your alpha units here, these little brown colored, and these are the beta units, but it's really not that important just to know that they're there. And you have all the structure, the primary, secondary, tertiary, and then finally the quaternary as all those 4 hemes come together. Now, interestingly enough, when you talk about the active site of the hemoglobin molecule, it's actually very tiny. The active site is a very tiny little area, and you can see the little red lines here. Roughly where the active site may be. Okay, so the active site is within each of the subunits, and it's a little area. And what I'm going to do is I'm going to kind of zoom in on this active site a little bit here and show you what's going on. So this is a primary component of the active site here. And just like I've talked about in other videos, black is carbon. My blues become nitrogens. This is an iron atom, and I'll talk about the structure of what's going on here. So this is what's called a porphyrin ring, and the porphyrin ring sits inside of basically the little active site within the hemoglobin molecule, and within the subunit, and then you actually, so it kind of is like a little cave, if you will. Kind of imagine that this is sitting engulfed in a little cave, and you have other chains coming out of that as well. Okay, so it's just not sitting there by itself. Okay, so you have your porphyrin ring, you have your nitrogen atoms, and then you have an iron atom here in the middle, and this iron atom is not covalently bound to the nitrogen atoms. They're not covalently bound in the the classical understanding, the classical definition of what a covalent bond is. These are actually, the nitrogens are actually coordinated with the iron. So this is a coordination complex, and if you're not quite sure what that means, I would say, hey, go ahead and review my my series of videos on crystal field theory and inorganic chemistry, and that will give you a little better idea. Crystal field theory is one way of looking at the coordination complexes. There is actually ligand field theory, which is the proper covalent kind of theory, but yeah, it's a coordination bond, and just like we talk about, a lot of your inorganic complexes tend to have tetrahedral geometry. That is to say that there are 6 ligands that can interact with d orbitals that have been split in energy levels when looking at the metals, your transition metals. So you have iron, and iron is coordinated with these 4 nitrogens here, and that's handy because the nitrogens, of course, have lone pairs of electrons. The iron exists in it's not its state that you find iron in nature. It actually exists in oxidation state. It's +2, which is the I believe the ferrous is the ferrous state is a +2 oxidation state. So obviously there's going to be some electrostatic attraction between those lone pairs of electrons, and then the iron down here is covalently bound. Okay, I believe to like a histidine. I think it's a histidine residue that attaches to the rest of that. That globulin there. Okay, so when you look at this, the iron atom sits slightly below. If I were to kind of show you this straight on, you see how the iron atom is kind of slightly below the plane. Okay, slightly below the plane of the porphyrin ring here, and that's actually really important. And this is a proper covalent bond. It's pulled down, and then it's coordinated with these 4 guys here. So I have 1, 2, 3, 4, 5, basically 5 bonds, and in coordination chemistry, talking about tetrahedral structure, there's an open area here where a ligand can come in and interact. So you have this kind of sitting in here, surrounded in this little man cave, and then you have an oxygen molecule. Okay, oxygen molecule, 2 oxygen atoms, double covalently bound, and then if you just typical Lewis dot or valence shell electron pair repulsion Vesper theory, or more traditional, conventional chemical theories predict that you have 2 lone pairs of electrons, lone pair here, lone pair here, lone pair here, lone pair here, and then you have your double covalent bonding going on here. So those lone pairs of electrons on the oxygen, of course, could be attracted to the iron. And so what's going to happen is, and remember, this is kind of in its own little man cave, and there are other little things that are coming out that interact with this oxygen. So basically what happens is the oxygen comes in, it doesn't just plop right down on top of there. One pair of the lone pair of electrons on this molecule, one of those pair will coordinate, okay, with the iron, okay, and then you have these other things here that are interacting with it, and the oxygen actually kind of, if I were to show you this, it actually kind of comes in at an angle. It doesn't come straight on. It comes in at an angle, and that kind of makes sense because we're coordinating with just one of the lone pair, and you have these other intermolecular forces that are acting upon the molecule as well, these non-covalent forces. Okay, so oxygen is going to come in at an angle, it's going to coordinate with the iron atom, and when it does that, the iron atom actually gets pulled up a little bit. First of all, the iron atom goes from its ferrous, which is the +2 oxidation state, to the ferric state. It becomes oxidized, and it takes on a +3, which is, I believe, the ferrous state. I get ferric and ferrous mixed up, so if I happen to mess it up for this video, I just kind of deal with it, and call me out in the comments. I'll be more than happy to post a correction. Okay, so what happens is that oxygen atom gets pulled up back into the plane, okay, the plane of the porphyrin ring. is normally it's down here below, it gets pulled up, and that pulling up causes some other things to happen. Let me get my computer going again. Maybe one of these days I'll go to a proper computer that doesn't give me problems every 5 minutes. But that iron atom gets pulled up into the plane, and of course that's going to act on here on this histidine residue, which is going to then pull on another part of the, and basically you have the kind of this long chain of events that's translated basically, and it's just a tiny little movement we're talking about, but it's basically translated throughout basically the entire molecule of hemoglobin. And what that does is that changes slightly, ever so slightly, changes the conformation of these other these other subunits, the other alpha and beta subunits. And when they have that conformational change, just that when you have oxygen binding to just one, this is where you get that allosteric cooperativity, or the allosteric effect that happens when one oxygen binds to a hemoglobin molecule, that translate to changes that actually increase the affinity, the binding affinity of the other three. So once you get that first oxygen, and I've talked about this in other videos, I just haven't gone into the chemistry so much of it. It's going to left shift the hemoglobin molecule as oxygen bonds. It's going to left shift, and it's going to make the other three hemoglobin molecules want to bind to oxygen. And that's where you get that kind of that allosteric cooperativity that occurs through just that, that one oxygen coming in, pulling that iron up, that iron pulling up a little bit on the histidine residue, and that little movement being transmitted throughout the entire hemoglobin molecule. Okay, so that's normally what happens, oxygen bonds. And then when you get to tissues that need oxygen, of course, you have the Bohr effect, and you have a change in pH, a lowered pH, or increased levels of 2,3-diphosphoglyceride, 2,3-DPG, which is kind of like a little crowbar. But there is signaling. There's a signaling mechanism that decreases the affinity of hemoglobin for oxygen and allows oxygen to leave. The iron gets pulled back down, the oxygen leaves, the iron goes back into its +2 oxidation state. And then one oxygen molecule leaves, and that makes the other subunits more prone to release their oxygen. You have oxygen release, and then the oxygen, and then the hemoglobin circulates into the lungs. You have different pH in the lungs. You have less DPG, and you basically have a left shift that occurs, and it goes into the tissues. You have a right shift, and you have this kind of this Bohr effect, this Haldane effect, and the pH changes regulating hemoglobin releasing oxygen, and onloading and offloading oxygen. Okay, so I basically wasted about 15 minutes or so of everybody's time talking about how oxygen binds. But now that we know how oxygen binds, and we know a little bit about the chemistry, a little bit about this allosteric cooperativity, let's now talk about the carbon monoxide molecule. This is carbon monoxide. This isn't totally accurate because my molecular sets, you basically have, it's a triple bond here. Not a double bond, but hey, I can't represent the actual chemistry. There's some really interesting hybridization that goes on here to make the carbon monoxide molecule. We know that this is it's the normal combustion product, or some people say it's an incomplete combustion, but it's just a normal molecule that occurs anytime you have organic combustive processes occurring. Now the carbon monoxide molecule, okay, can also coordinate with the iron. Actually, there's about 230 to 250 times the affinity. Okay, so carbon monoxide has a much higher affinity, or the hemoglobin has a much higher affinity for the carbon monoxide molecule. So when it comes to oxygen versus carbon monoxide, obviously carbon monoxide has a significant advantage when it comes to binding the active site. And up to this point, this probably isn't anything new for anybody, okay? Nothing new. So the carbon monoxide comes in, it binds, and most people kind of stop there. They like go, hey, you know, it has a higher affinity, it binds, and now that the carbon monoxide is bound, oxygen can't bind, and you don't have the ability to carry and transport oxygen. End of story, you die, or you get really sick. However, there are other things that occur here, because a lot of people neglect to say that yes, carbon monoxide does prevent oxygen from binding, but think about this. If you think about this for a minute, when oxygen comes in, okay, oxygen kind of comes in, it causes an allosteric change. Do you think that perhaps carbon monoxide could also cause or interact with the allosteric cooperative mechanisms? And the answer is absolutely it does. It does in a marked way. And what it does is carbon monoxide comes in and it binds, and it induces a very strong left shift. It shifts the oxyhemoglobin dissociation curve to the left. It markedly increases hemoglobin's affinity for oxygen. Okay? So let's think about this. If I have a marked increase in the affinity of hemoglobin for oxygen, does that mean that carbon monoxide totally prevents oxygen from binding to hemoglobin? Well, absolutely not. In fact, oxygen, there's a better affinity. Oxygen, if there are open sites available, oxygen is going to bind to hemoglobin. It's going to readily bind to hemoglobin. But here's the problem. Because there is such an extreme left shift, the hemoglobin is not going to offload the oxygen at the tissue level. So when we talk about carbon monoxide toxicity, it's a kind of a 1-2 situation here. Yes, there is a competitive mechanism where carbon monoxide is binding in place of oxygen. Okay, so you have a decreased oxygen carrying capacity of hemoglobin, but a major part of that mechanism, the other side of that mechanism, is that the oxygen that is bound to hemoglobin does not disengage. The hemoglobin is so left shifted that it holds on, it's locked onto that oxygen and does not allow what oxygen is bound to hemoglobin to be released. So it's a 1-2 mechanism that goes on, and a lot of people don't, some people, I don't say a lot, but some people, when they talk about carbon monoxide, don't actually touch on the other part of the pathophysiology, or the known pathophysiology of carbon monoxide, is that yes, there is an anemia that occurs, or a hypoxia that occurs due to the inability to load, or due to inability for hemoglobin to load oxygen. But the other part of that is the oxygen that's bound to hemoglobin is not readily available to be released. It's not being able to be released. Now, with all of that said, there are some other things that go on, and when we look at the research and we look at patients and we measure their levels, what we call their carboxyhemoglobin levels, the amount of hemoglobin that's bound with carbon monoxide, we find some interesting things happening or occurring here. We find that carboxyhemoglobin levels don't always correspond to the clinical presentation. There is not a standard dose response curve, if you will, okay, where there are many reports of people that have very high levels, significant levels of carboxyhemoglobin that are relatively asymptomatic or have mild symptomology, mild signs and symptoms. And then there are many reports of people that have very low carboxyhemoglobin levels that are markedly symptomatic and go on to have marked neurological, life-altering experiences as a complication of the carbon monoxide toxicity. So clearly, the hypoxic mechanism that people always quote, clearly that is not the entire picture. There are other mechanisms going on, and we don't have a really good idea. Some of these mechanisms, we look at the areas of the brain that get damaged, or we look at areas of the brain that are changed. Looking at autopsies, magnetic resonance imaging of the brain, we find that the areas of the brain that tend to get damaged in carbon monoxide toxicity are what we call watershed, quote unquote, watershed areas, where they're not as highly perfused as certain other areas. And so there are some hypotheses that are out there that carbon monoxide may actually affect cellular perfusion, may affect how blood flow occurs and where blood flow occurs, in addition to the other things. And that may be through possibly through modulating nitric oxide pathways or some mechanism similar to that. I don't really know, and I'm not sure that anybody would be confident in saying that they know. But at the end of the day, the toxicity of carbon monoxide is much more complex than a lot of people would admit or would say that it is. That the elucidating the mechanism is not nearly as simple as sometimes it comes off. So there you go, long video talking about something that a lot of people know about in healthcare, but hopefully there's some new things conveyed here. And I'll see you guys in the next video, and as always, thanks for hanging in there.